But we're continuing memory latency tolerance. An announcement, my office hours have moved today. It turns out this room is a good room for faculty candidate seminars, and we have another faculty candidate coming up after this, so I have to attend that talk. If you're more than welcome to attend also. I think one of you did that before. Okay, this is a reminder on the assignments. You know all of this, right? Hopefully. Hopefully you're enjoying the simulation of data cache and branch prediction at the C level. Some news for you. Is this a good day? It works, April 22nd. That's Wednesday. So mark it down on your calendars. But there aren't many other good days, frankly, on the calendar. And this is a reminder on the usual stuff. It'll keep moving quickly. But again, my goal is to enable you to learn the material. So hopefully what you will take out of it is really the material and not care much about the grades that you get. In the end, if the material sinks in a little bit late, that's OK too. My goal is achieved, right? That's OK. That brings me to lab late days. Since my goal is to enable you to learn the material, I'll give you 3 more late days for lab 6 and lab 7. Is that good? Yes. Yeah? Yes, these are exclusive. Well, no. I mean, if you have not used any of your late days, you can still use them on top of these 3, obviously. But you cannot use these for lab 8. There will be special treatment for lab 8 since it's due the last day of classes, right? And I'm willing to give you flexibility on lab 8, but you cannot use indefinite number of late days for lab 8. Otherwise, we would be out of the bounds of the semester, right? This is a boundary condition problem. How many of you have not used any late days? We can be proud. Yeah? That's good. And you've submitted the assignments, right? Yeah, obviously. Because there's one way of not using any late days, not submitting any assignments. But that's good. I saw that some of you were over the late days, actually, which is OK. I mean, even if you're over the late days, please keep submitting. Again, the goal is not to ding you on how late you are. The goal is really to enable you to learn the material. If you submit it, I don't know, if you submit lab 7 maybe later, that's also OK, because I want to see. Now, that said, you know how many late days you have remaining, right? Everybody knows that very well. You're keeping count of it every day. So if you have late days remaining, I have a present for you. It's from Turkey. Remember, I went to Turkey for a conference. And it's a different kind of Turkish delight. So say it again? Is it baklava? No, it's not baklava. Baklava would be relatively stale by now if I had gotten baklava. Although next time I'll try that. Sure, that's a good idea. But this is Turkish delight. It's actually a different one than you had last time. So who will have the pleasure of opening it? No, I guess you'll do it. Take as many as you have late days. If you have 10 late days, take 10 of them. I don't think we'll have a problem running out. And if you owe me late days, then, well, I guess no one will owe me late days if we assign 3. But you can still take them. Don't worry.
Does this include the newly given late days?
Oh, that's a good question. Well, how many people do we have here? Yeah, it does include, sure. But you may not get the quality of service you want because there are different kinds over there, and somebody may take up the best kind over there. But the best kind depends on who you are. That's a classic resource sharing problem, right? Yeah.
For application aware, then everyone could take just one of each, and we'd all get.
That's right. Yeah, you can be fair. Try to take one of each over there. Try to have a fair distribution. That way you can sample. OK? If something is remaining at the end, we'll do a best effort distribution. So everybody takes their quota, which is the number of late days you have left, and best effort distribution at the end. And TAs can take, I guess TAs will take the best effort. Poor guys. Maybe you can donate some of these to the TAs. OK. Where we are in the schedule, we're covering memory latency tolerance techniques, and we'll cover some more today. And I'd like to remind you, very, very related to what we've been covering, caching, prefetching, latency tolerance. There's a talk on Friday that combines a lot of these issues, actually, and also talks about some new memory technologies, 3D stacked memory technologies. So I would definitely encourage you to attend this talk. from 11 a.m. to noon on Friday. And we can walk back from there to class, hopefully after that. Okay? It should be a good lecture that kind of brings together all of the concepts, a lot of the concepts we've been seeing in the context of modern systems. Well, everything we've been seeing is applicable to modern systems, but this is on technologies that are coming up, like 3D stacked memories. OK, you know the required reading. How many of you have done it fully? That's good, at least a few. Is there a good summary? Yeah? I guess you're writing a summary of it as part of your assignment, so I'll read them. Or you have already submitted them, right? OK, good. Then I didn't see enough hands. How many of you have done it? OK, that's more. That's good. OK, so let's talk about let's talk more about tolerating memory latency. Remember, this is the picture I showed you. This is actually circa 2003 on data-intensive applications. Most of the time, the processor, a very aggressive out-of-order processor with 128 instruction window, spends most of its time waiting for memory. Yeah. And this is increasing going forward, actually. That's the unfortunate fact of life. Now, is this true for all applications? That's absolutely not true, right? There are applications that fit nicely in the cache, and you're not waiting for memory, as much at least. You may be waiting a little bit to fill your cache. But this is true for a lot of very, very interesting applications that are already present and that are going to come up going forward. And your reading kind of talks about that, motivates that also, right? So how are we going to tolerate this latency? And we've covered this slide, so I'm going to go through this really quickly. Basically, we covered caching in the lectures a lot. And the talk that you're going to see on Friday is about caching, actually, with a different technology. Multi-threading, we've covered some. Actually, one of the benefits of multi-core processors is also tolerating memory latency, right? If you actually have a single core, maybe it's difficult to tolerate this latency because of what we discussed, right? Scaling the instruction window size is difficult. But if you actually have smaller cores and replicate them, and hopefully put the burden on the programmer and say, the programmer, why don't you parallelize this program? All of those cores can generate a lot of memory accesses such that you can overlap the memory accesses generated by one core with the memory access generated by other cores, right? So we can view multi-core as a method to tolerate memory latencies. And many people have actually thought about it this way. So multi-threading, multi-core is a special example of multi-threading, in a sense, right? You have the threads running on separate cores instead of threads sharing a single core. And out-of-order execution is another latency tolerance technique. And we've talked about how to scale it to larger sizes without larger instruction. We've talked about how to get the benefits of having a larger instruction window by keeping the instruction window size small. And that was the idea of run-ahead execution. And just to jog your memory very quickly, basically, this is a technique to obtain the memory level parallelism benefits of a large instruction window. And when the oldest instruction is a long latency cache miss, you go into this speculative processing mode called run-ahead mode after checkpointing the architectural state. During this mode, you speculatively execute instructions just like as in normal mode, except it's purely speculative. You don't update any architectural state. You don't update this checkpoint. And the purpose of this pre-execution is to generate prefetches. And the stuff that's dependent on cache misses, L2 misses, are marked invalid and dropped because you don't have the data for them. But everything else you can execute to actually hopefully generate some cache misses, which can be serviced in parallel with the original cache miss. And this mode ends when the original miss returns. And then hopefully, when you re-execute the program, you'll get to some those load instructions that you've generated early, and their data is already in the cache. And then you don't stall. OK? And you basically, you restore the checkpoint. That's how you actually continue execution. And this was the picture that I gave you, right? Instead of stalling multiple times for different loads, because your instruction window size was not large enough to bring in this load into the instruction window and generate this cache miss, you basically stall once for the original load. But instead of stalling, you speculatively pre-execute, pre-process the instruction stream, and generate the cache miss associated with the independent load 2, such that you can parallelize the accesses that are generated by these two loads. And when you really execute this load 2 after the end of run-ahead mode, you get a cache hit for that load. Kind of nice, right? I like this. I worked on it for a long time, so I should like it. But others have liked it also. So this is kind of the nice thing about simulation and how research affects industry, right? If you actually do the simulations right, with an insightful technique, hopefully, you don't need to go into the all design layer, right? Real design. So I never did a real design of run-ahead processor, but other people have done it. They've taken the results and they've actually implemented something very similar to this in Sunrock and IBM Power 6, and hopefully more. Who knows? And there may be other things that I don't know of. OK, so how do you enhance it? I'll very quickly talk about some of the problems with it. Whenever you have an idea, it's always good to make it even better, because there are issues with it, as we've discussed, right? One of the issues is energy inefficiency, for example. A large number of instructions are speculatively executed. I'm not going to talk about solutions to this, but I'd like you to be aware. And the problem is because you go into this run-ahead mode, you execute lots of instructions. And for example, if you don't generate any cache misses during that mode, you go back and re-execute all of them again, right? And it's useless in that case, right? You're just increasing the number of instructions you executed for no benefit. Sounds like a bad idea, if that's the case, right? Yes?
But that doesn't have to be, right? Because if they were independent instructions, then they don't have to be re-executed.
That's right. But if you use the run-ahead as we've discussed, so now you're finding potential ways of overcoming that energy efficiency problem. If you actually find a way of reuse those results and not re-execute any of them in a good way, then you fix the problem. You're right. So that's one potential fix to the energy efficiency problem. Another potential fix could be, maybe that's more complex, right? Because now you need to save those results somewhere and then integrate them back when you finish the run-ahead mode. Now, one of the problems with that approach is it's not as nice anymore because run-ahead mode is not purely speculative, right? If it's purely speculative, now you can say, oh, I'm going to ignore a lot of stuff. My goal is to just go ahead in the program and get cache misses. But if you're trying to save results, then you need to ensure that those results are correct so that you don't re-execute them. So that puts some burden on the designer.
That's more like out of order.
That's right, exactly. What you're saying is somehow try to build another kind of out-of-order machine by saving those results. Yeah. Maybe there's a different way to do it. But yeah, I like the way you're thinking. Yes?
I mean, if we're just generating cache misses, so we're looking for lows and stores, right?
Yeah.
And we're already prefetching the next instructions. So why can't we just jump to the next load immediately after run-ahead mode?
So these are actually really, really good ideas. We've explored a lot of these. But how do you jump to that load? Because you have state at this load, and you need to somehow execute those instructions in between. And this load's address is affected by some of those instructions, right? So you need to execute at least some things. The key question is, what do you execute, right? And we'll get to that, actually. Toward the end of this lecture, we're going to talk about thread-based execution prefetchers. Execution-based prefetchers or thread-based prefetchers, which try to do something like that. Figure out what needs to be executed and then generate a thread for it and then execute it. OK, now you guys are trying to solve the problem, which is good. Basically, one other solution to the problem, a very simple solution, not complicating things. You can say, oh, maybe I can detect these episodes where I don't gain a lot of benefit from run-ahead mode. And I predict them. And I say, oh, for this load, when I get a long latency miss, I should not enter run-ahead mode. Because there's nothing that I'm going to gain out of that run-ahead mode, right? You can learn from the past again. That's a very simple solution. Actually, some processors employ it. OK? So I'm not going to talk about these solutions. You can actually look at this paper if you want to think about see some of the solutions. I'll talk about the second one because I think it's very interesting. It ties in nicely to what we were going to talk about with prefetching. One of the problems with run-ahead is it's ineffective for pointer-intensive applications, right? Why? Because remember this load 2 over here? If this load 2 is actually dependent on load 1 through some execution, you cannot actually generate this cache miss over here, right? Because you don't have the data of load 1 in run-ahead mode. So how do you make it effective, actually, for pointer-intensive applications? I'll talk about that in a little bit. But there's also, yeah. No question? OK, I thought somebody was asking a question. And the last thing we briefly talked about is you can have irresolvable branch mispredictions in run-ahead mode, right? For example, if you have a branch that you're executing in run-ahead mode that's dependent on this load miss, it'll be invalid, right? And if you predicted it correctly, that's great. You don't know. You cannot resolve it, but you're still on the correct path. If you mispredicted it, then it may make sense to recover and go on the correct path, right? But then how do you do it? Remember, in the last lecture, we've discussed if you cannot do that, it's OK to keep going on the wrong path, because wrong path may actually prefetch useful stuff for the correct path. And there's a lot of analysis in literature that indicates that wrong path, going on the wrong path, if you don't have the alternative of going to the correct path, is a good idea, because you actually generate useful load instructions that prefetch data into the caches. But maybe you could do something else. And this is actually a really interesting idea. Potentially, you can guess that you're on the wrong path, right? And this is where maybe you guys can develop ideas too. But how do you guess whether you're on the wrong path? Well, what if when you're executing down this path, you get a null pointer? You're loading from address 0, let's say. Maybe you're on the wrong path, right? And if you're not on the wrong path, maybe the program is wrong anyway, right? So maybe that's a good indicator of the fact that you're on the wrong path, right? So actually, this paper that you may want to read talks about some of the other things. For example, another indicator of wrong path is if you see lots of branch mispredictions in a row. That may be an indicator of the fact that you are on the wrong path. It turns out, if you see lots of branch mispredictions, it's likely that you're on the wrong path. Lots of BTB misses. It could also be an indicator of phase change in the program. But if you're in run-ahead mode, you don't care, right? Maybe you go back to that location. OK. Let's talk about this dependent cache miss problem, because this is actually one of the very difficult problems in computer architecture. Somebody once said, in single-core design at least, in single-core design, there are only two big problems. I don't necessarily buy this, but this kind of reflects what industry has worked on for a long time. One is predicting branches, figuring out where branches go. Second is prefetching. And prefetching kind of relates to this, right? If you actually come up with really good techniques for these, you're golden. You can be a millionaire. Actually, when at the heydays of branch prediction, when Intel wanted branch predictors, they hired this person that I'm not going to name that came up with a really, really optimized branch predictor that was called BLG, bimodal, local, and global. It was actually a very nice branch predictor that, at that time, it was an optimized branch predictor. And I think he was hired for a lot of money. Not that I encourage you guys to do that, but you can actually choose that path if you're a good architect, right? OK, let's take a look at this. I don't want to derail that much because I have a lot to cover. But if load 2 is dependent on load 1, it causes issues. Like when you get to this load 2 in run-ahead mode, assume that we're in run-ahead mode here, it cannot compute its address because it's dependent on a register that's invalid. As a result, maybe nothing happens in run-ahead mode. Nothing interesting happens. You don't gain benefit. And after you exit from run-ahead mode, you flush the pipeline. That's what this red box is over here. You refetch starting from the program counter that you checkpointed, and load 1 hits, because that's why you exited run-ahead mode. And then when you get to load 2, it can now compute its address, but it gets a cache miss. Well, and then you start running ahead again, right? Now, there are two downsides to this. First of all, it cannot parallelize. You were not able to parallelize the dependent misses. So you waste the opportunity to improve performance. If you actually parallelized, you could improve performance. You also waste energy, right? Because now you're doing useless pre-execution. In fact, you're executing some instructions again, right? You've executed probably a lot of these. And then you're executing a lot of those again, right? Because you're really starting from load 2 over here. Does that make sense? Yeah. So actually, this is one of the beautiful things about simulation again. You can take a simulator and say, oh, when I'm in run-ahead mode, yeah, I know that a real run-ahead processor cannot compute this address. But in the simulator, I can cheat. I can say, because we have the functional simulator at the front end, right? I can run that, and I can compute the address of the load. And I can say, oh, I'm going to use that address in my simulation, in my timing simulation, and generate that cache miss. And if you do that for all of the invalid loads that you encounter in run-ahead mode, your simulator, or our simulator, told us that you could actually improve performance by 25%. That's one thing that high-level simulation enables you to do, right? You can see what is the potential of developing a technique that could actually bridge that gap between the current state and the potential you can achieve. So that's what we did. And how do you actually solve the problem? Basically, there is good potential, at least with some workloads, right? You're always the slave of your workloads, if you will. If you don't choose the right workloads, maybe you'll never see the problem also. But then workloads are a function of what you care about as well, right, in the end. So on some workloads, so take this with a grain of salt, on some workloads actually you will see that the benefit is much, much larger. In fact, there are some workloads that are not that well written, but you could actually, if you parallelize these cache misses, you can actually get 10x or 15x performance improvement. You can take a look at some of the papers about that. OK, so how do you actually fix the problem? Well, you've seen the idea before, right? If you can actually somehow predict the value that's going to be loaded by this load, and if you get it correct or almost correct, you will actually enable the execution of this load too, and hopefully generate a cache miss associated with it. Basically, predict the values of L2 miss, address, or pointer loads, right? You may not want to do this for all loads, but if a load is going to actually generate an address or load an address into its destination register that's going to be later used downstream to compute the address of some other load, this may be a good idea. Now, we'll get back to this address pointer loads. How do you figure out what's an address load, what's not? But this is a load that loads an address into its destination register, which is later used to calculate the address of another load, right? As opposed to a data load, which is just loading data. OK. So basically, this is what we would like to achieve. When we get to this load 1 miss, when we enter run-ahead mode, we actually broadcast a predicted value for this load, assuming it's loading an address. And when load 2 is fetched in run-ahead mode, when it gets to the execution stage, now it can compute its address. And if the value prediction is correct, then it can generate a cache miss. And when you actually re-execute the load, it hits. So you save cycles. And you also save a lot of useless execution over here in the run-ahead processor. Sounds like a good idea, right? Now, the question is, how do you do this prediction? Well, I'll give you one idea. You can imagine many, many other ideas, right? But I'll give you one idea and then demonstrate why it may make sense. And again, this is the beauty of high-level simulation. And when you do high-level simulation, you can actually figure out these characteristics of the program. Basically, I'll give you how it works first and then talk about why it makes sense. So let's define the address value delta of a load instruction as the effective address of the load minus the data value of the load. Does that make sense? You're actually loading from an effective address, and the data value is what you load from that address. And it turns out for some address loads, for some loads that are loading addresses, this AVD is stable. Can you guess why? Maybe? It's always constant. Let me actually show you. Oh, that's not what I want. I want this. But don't seem to. OK, there you go. Maybe you can think about it a little bit while I. That's latency tolerance. You doing thinking while there's latency. What's happening here? And rotate 3 times. And what is that, do you think? Oh, actually, we can see you by doing this. Huh? Never thought of that. Oh, OK. Yes. One more rotate. No? One too many, huh? OK. So basically, what we're doing is this. Let's say we're loading into R1 some address. So this is your effective address, the computation that you do over here. And eventually, you'll get a data value over here. And AVD is essentially effective address minus the data value you load. And I'm saying that this is a constant for some loads. You execute this load once, you get K. You execute it again, you get K in a loop, let's say. It's interesting. For some address loads. And assume that this is true for now. You can design a predictor that keeps track of the AVDs of address loads. You say, oh, this load is loading a pointer. So I'm going to compute the AVD after it's executed. And the next time I get to this load, I can compute its effective address, right? But it gets a cache miss, so I don't know the data value. So I'm going to simply predict the data value as effective address minus K, right? Basically based on this equation. Assuming you recorded K in a previous execution, because in the previous execution you figured out both of these. And the next time you execute, you know the effective address. You recorded the K. You can predict the data value that way. That's one way of predicting the loads. And when a load is an L2 miss in run-ahead mode, you consult this predictor. And if the predictor returns a stable or confident AVD for that load, the value of the load is predicted just like I told you over there. Make sense? It's magic? Yes?
Yeah, but the address itself is predicted by them, right? Because you predicted the value of the first miss.
So what do you mean you predicted the value of the first miss?
When you were saying you get the first cache miss, you predict the value to take the second cache miss.
That's right, exactly.
So the EA at that point is predicted.
No, EA is computed, right? When you enter run-ahead mode, you know the address of the load.
Data value is predicted.
Exactly, data value is predicted. You predict the data value. You can also predict the address, but you don't need it in this case, right? Because you already have it. OK. OK, does this sound like magic? Not really, actually. It's pretty simple. Why it works is relatively easy to understand, because there's regularity in the way data structures are allocated in memory and traversed. I'll give you one example, which is, well, I'll give you two examples, actually. One is traversal address loads. These are basically loads that produce addresses that are consumed by address loads. This is best understood by an example. Let's assume that you're actually traversing a linked list. And it's regularly allocated, meaning each node is separated from each other, from the next node, by a constant number of bytes. And this is what your linked list looks like. This is the pointer to the current node. This is the pointer from the current node to the next node, ... And this is the address. This is the address of the current node, A, address of the next node, A plus K, address of the next node, A plus 2K, address of the next node, A plus 3K. Why does this happen? Because you have a linked list of nodes that happen to be allocated side by side. And that's actually what may happen when you allocate a regular linked list, right? OK. So if you are traversing this linked list, what you're doing is this, right? At the C level, you write code like this. You basically load the pointer to the next node by doing this, by dereferencing this next pointer. Let's take a look at what happens to this load when you execute it. Let's take a look at its AVD, which is effective address minus data value, right? So the first time you execute this load, its effective address is A. That's the address of the node. And the data value that you load is the address of the next node, right? A plus K. So AVD is minus K. The next time, you go into the next node. And you're looking at this one. The effective address of the load is A plus K. The data value is A plus 2K. And the AVD is minus K again. Next time, minus K. That's how you get predictable address value deltas. Even though yeah, you have a stable AVD. There's another way of predicting it, which is looking at the data values, right? Now remember we had a discussion on value prediction? Well, this is why value prediction actually works. If you look at the values, they have a constant delta from each other. So if you record the last value that you have in this load and the delta, which is the stride, then you can actually figure out what the next value, next data value is, right? Now, AVD is a simpler way of doing this, perhaps, right? Because AVD doesn't require you to know the last value, even. OK? So you can actually predict the data value of this load just by recording the AVDs, in this case. There's another place where this could be predictable. And I'll give you one other example. This is actually a harder case. But programs have these cases. Let's assume you have a sorted dictionary. And this happens in one workload called parser. By the way, this happens in many, many workloads. If you're you can have a nice memory allocator that tries to do this, right? Tries to change the layout of your data structures such that you have a striding or streaming pattern when you're doing your traversals. People actually propose that. For example, some of the garbage collectors try to do that. Because what happens is you can actually, when you're running Java, for example, who runs Java? Who writes program? OK, good. We won't hold it against you. But but these are just-in-time compilation mechanisms, right? So if you do enough profiling, and the just-in-time compilers can actually put code that can profile and figure out the access patterns. And if the just-in-time compiler figures out that a linked list traversal is really hot, you keep doing it, it can actually analyze how this linked list is actually allocated in memory. And the next time garbage collector is invoked, it can tell the garbage collector, look, I'm traversing this linked list, and the nodes seem to be all over the place. Why don't you put them together and give me a nice regularly allocated linked list? If the garbage collector actually does that, now the next time you actually traverse that linked list, well, first of all, hopefully your prefetcher would work nicely. And maybe your cache works nicely also, because you could have multiple nodes in the cache, assuming these nodes are small enough. And this mechanism, this value predictor, would work nicely also. So there are a lot of benefits of laying out data structures that you traverse frequently close together in memory. OK, let's take a look at another example. It's a more difficult example, as I said. This is from a dictionary. And a dictionary may look like this. Let's say you have strings. This is what you're actually storing in your dictionary. And nodes are stuff that actually point to strings, because you dynamically allocate these. And you can actually form your dictionary dynamically by actually forming a tree, right? And you form it dynamically. And eventually, because you want it sorted, in this case, it's a binary tree, right? Basically, words that are greater than or larger than this are here. Words that are smaller than this are here. And you can balance the binary tree such that your searches are minimized, right? So when you look up this dictionary for an input word, basically you execute some traversal load, certainly, right, to traverse through the nodes. But you also do this, basically. To be able to load the string, you do this kind of dereference. Basically, when you get to this node, you need to dereference the string. OK, let's take a look at this particular load. I'm not going to look at the traversal load here, because that's actually difficult to predict over here. But again, if you have a regularizing allocator, maybe you can fix that problem also, assuming that your dictionary becomes stable at some point. So let's take a look at how this is executed. So the first time you see this load is when you traverse this node. The effective address of the node is a plus k. And the data value that you load is a, right? That's basically the pointer that you're loading. And the AVD is k. The next time, let's say you're searching for some word that happens to be over here. The effective address of the node you're visiting is c plus k. And the data value is c. That's the pointer that you're loading. And AVD is k. And the next time, let's assume that this was the word that you're searching for is smaller than this. The effective address of the node you're visiting is f plus k. And the data value, which is the pointer, is f. So your AVD is k. Again, your address value delta is stable. But here is one place where your stride predictor wouldn't work. Right? Assuming that these ACF have no relationship with each other, they're kind of randomly allocated, then you cannot predict the value of this particular load with a stride predictor. Make sense? OK. OK. So how do you actually identify these? Now that we've shown that there are some stable address value deltas in the program, remember I said that we would like to do this for address loads only, loads that are loading pointers, addresses, into their destination registers. And how do you actually identify these? One way of doing this is actually, I mean, if you look at this, the language kind of tells you that, right? The compiler can easily figure this out, because hopefully, well, you're loading a pointer over here. The compiler knows the type of this. And if you have a bit field indicating that this load is actually loading a pointer, you know that information, right? Unfortunately, that doesn't exist in existing systems. A lot of people have proposed. A lot of people want it, because it'd be good if you know whether you're loading a pointer, right? That maybe you can actually do prefetching. We will see that in a little bit. But assuming that you don't have that information, how can you actually figure out whether a pointer is loading an address or something else? Well, there's an insight. If the AVD is too large, then maybe the value that you're loading is not an address. Again, this is a prediction. Why does this make sense? Because if you look at the AVD, I'll call this the AVD. What you're really doing is you're taking effective address, you're subtracting the data value to it. Let's look at this effective address. Effective address has some number of bits. Let's say, I don't know, 64 bits, right? And the data value that you have is another 64 bits. An effective address basically tells you where in memory this thing is allocated at. So maybe it has 5ff ... some location, right? If it happens that the top bits of the effective address actually match kind of the top bits of the data value, it's likely that this data value is also an address, right? Because addresses happen to be allocated from similar places. Make sense? So that's kind of the insight over here. It doesn't always work, obviously. But if AVD is less than some maximum value and greater than some minus of that maximum value, then we're going to predict that this load is actually an address load. It's loading a pointer. Whereas if you're actually, let's say you're loading from 5FF and this is all zeros, well, probably that's not a pointer, right? Or this is 0, 0, 0, 5 at the bottom. Again, probably that's not a pointer, right? So this exploits the observation that pointers are actually coming from similar parts in the memory address space. We'll get back to this, actually. Some other people made this observation and proposed a really cool creative prefetcher for this. But now you can actually say, whenever you compute the AVD of a load, you say, oh, if the AVD is too large, then I'm not going to even allocate a predictor entry for this. So you can actually have a really small predictor. And no need to value predict the loads that will not, or that are predicted to not generate addresses. So what is the performance of this? Let's take a look at it very quickly. You can read the papers for actually more analysis. You're not required to. As long as you get the gist of the ideas over here, that's good. Basically, this is some applications that actually have some pointer chasing that happens. And this is, for example, a minimum spanning tree. It computes the minimum spanning tree. This is by sort. This is the traveling salesman problem. So a lot of the graph-based algorithms, basically. And you can figure out what the rest are. This is a terribly written program. It's called Health. I think it does scheduling. It does doctor-patient scheduling for the health system. Somebody didn't write it well. But if you look at it, this is the execution time normalized for a run-ahead processor. And this is the performance benefit you get. Basically, this is the execution time, the blue one. The performance benefit you get on this application is like 5x, more than 5x, right? You reduce an execution time of 1.0 to 0.2 or so. OK? So it can actually benefit a lot. Now, the alternative could be go and rewrite the program such that it doesn't have these dependent loads, right? Well, that may be not so easy to do, especially for non-hardcore programmers. You guys should be able to do it easily, but not everyone. So this also reduces execution instructions as well. So the average may not be representative of all programs over here. You can actually reduce the execution time significantly on top of run ahead, as well as execute instructions on top of run ahead. Does that make sense? And one of the other things, if you have a purely speculative execution mode like this, you don't have to be perfectly correct, right? If your AVD prediction is incorrect, again, it doesn't matter. Right? It doesn't matter in terms of correctness. Maybe you miss the opportunity to improve performance. But you already say, everything I do in this mode is speculative. So you don't need to verify it as much as well, because that makes if you need to actually be correct in run-ahead mode also, that increases the burden on the hardware designer. Okay. That's another beauty of prefetching. Prefetching, again, doesn't need to be correct. So we'll talk about prefetching now. OK, I'm looking at the wrong time, so we still have time to take a break. So you can do the best effort scheduling of the Turkish Delight if you want. Looks like there's some left. Yeah, sure. Feel free. OK, so this is kind of the outline of the prefetching lecture or lectures. We're going to talk. Well, we've been talking about prefetching, actually. Really, run-ahead execution is a form of prefetching, right? But I want to do a little bit more formal treatment of prefetching. And these are the things that we're going to cover. We're going to cover why prefetch, and hopefully this is going to go really fast. The 4 key questions: what to prefetch, when to prefetch, where to prefetch, and how to prefetch. And we're going to have a survey of different prefetching algorithms, most of which are employed in some form in today's systems, actually. We'll talk about some metrics to evaluate prefetching. We'll talk about prefetcher throttling. And probably you won't get to it, but you can imagine that prefetching can cause other issues in multi-core, like interference issues, right? We've discussed interference issues between cores when the cores are actually, assuming that the cores are actually demanding memory. What if one core has a prefetch request to memory and another core has a demand request to memory? Now the memory controller has a choice. Which one do I prioritize? Well, which one is more important? Again, it's not clear, right? You can say demands are more important than prefetches, so I'm going to prioritize demands over prefetches. Well, what if prefetching is really, really useful, right? And what if a prefetch is a robot for hit, and a demand is a robot for miss, or a robot for conflict? Now you have an even tougher choice to make, right? Because if you just service that prefetch, it'll be really quick. And if the core is actually going to demand it next time, maybe you'll get a robot for conflict. So it introduced a lot of interesting issues, which we're not going to be able to cover. But if you design a memory controller in the future, you're going to have to solve. OK, so basically, the idea we've discussed earlier, fetch the data before it's needed. Basically, pre-fetch or preload the data. Why? We've already discussed this, right? Memory latency is high. Again, this is a latency tolerance mechanism. If we can prefetch accurately and early enough, we can reduce or eliminate that latency. Right? Run-ahead execution example, the beautiful run-ahead execution example did that, right? It used the prefetcher, which is the out-of-order execution engine in that case. And it can eliminate compulsory cache misses. You may never have seen this block before, but you can prefetch it. That's the beauty of prefetching. Caching is a reactive mechanism. Basically, you have to have seen that block before to be able to cache it, right? Whereas prefetching is proactive, right? It can actually generate addresses that you've never seen before. Can it eliminate all cache misses? Capacity, conflict? Sure, why not? I'm asking you can, right? Yeah, because if you can actually somehow predict the access pattern of the program, you can eliminate all cache misses, right? There's nothing that can, I mean, you're really bound by what you can predict over here. And how, again, how accurately you can prefetch and how early enough you can prefetch. Even if you're not, so the best way when the prefetching works is you actually prefetch the data right before you really need it, right? That's the best kind of prefetching in a sense. Well, that may be difficult to do. What if you prefetch it a little bit early? What if you prefetch it a little bit late? May still be OK, right? If you're a little bit late, maybe you cover most of the memory latency, such that the load, when it really needs the data, it'll wait just a little instead of waiting for hundreds of cycles. But timeliness is an important problem, certainly. So this involves predicting which address will be needed into the future. And it works if programs have predictable misaddress patterns. So we've already discussed this briefly in run-ahead execution. Does the misprediction prefetching affect correctness? And the answer is no, right? Because prefetched data at a mispredicted address is simply not used. And you should not design a prefetcher that affects correctness. That's a bad idea. There's no need for state recovery. Then it won't be kind of a prefetch, right? OK. And this is in contrast to branch misprediction or value misprediction, right? If you have a branch misprediction, you need to recover the state. Because at least not in run-ahead mode, in normal mode, right? You need to actually recover the state. In run-ahead mode, again, if you're in a purely speculative mode, you can do branch mispredictions, value mispredictions, and never recover from anything. Because you're going to recover later on somewhere. OK. So in modern systems, and most of the discussion that we will have in prefetching, we're going to assume that prefetching is done at the cache block granularity. So we don't prefetch individual words, but we prefetch cache blocks. OK? And prefetching is a technique that can reduce both miss rate as well as miss latency, just like I described, right? You can actually have a prefetch that's a little bit late. You still get the miss when you actually need that cache block, but the miss is much shorter now. OK? And prefetching can be done by many people, if you will. Hardware, compiler, programmer. Have you guys done prefetching in your programs? It's fun to do. You can actually change your loop structures, for example, such that one loop is just for prefetching. It has lots of prefetch instructions. And the next loop actually does the operations, right? Have you done that? Yeah, you can do that, right? Especially in regular programs, it just makes sense to do, right? OK, so let's take a look at the hardware side. This is how a modern hardware prefetcher fits into the memory system, for example. This is the memory system, the baseline. You have iCache, Dcache. They share an L2, and then L2. And then in this case, we kind of assume that the memory controller is off chip. That's actually an old picture. It doesn't matter anyway. But if you look at the prefetcher, you have a choice. Even this one gives you what kind of choices you have. Where do you put the prefetcher? Right? Do you put it into the iCache? Do you put it into the Dcache? Do you put it into L2? Do you put it in the memory controller? Do you put it everywhere? Well, actually, everywhere is a good answer, because many systems have prefetchers almost everywhere today. But this is one example. You can actually put it such that it observes requests coming into the L2 and kind of tries to figure out patterns in them. Maybe like one pattern is A plus 1, A plus 2, A plus 3, right? And then you can also maybe figure out B plus 6, B plus 12, B plus 18. Modern prefetchers are actually even more sophisticated. So they can actually figure out, we're not going to talk about those, but you can imagine how to build a prefetcher for this. They can actually figure out deltas between the previous addresses that are different. For example, your deltas from the original address and your deltas between individual addresses could be +1, +2, +1, +2, +1, +2, +1, +2. Modern prefetchers can actually do that. And they're going to use the principles that we discussed, but you need to actually optimize the design. So this is where it can actually fit. And then prefetch requests can be queued, and then they can access L2 afterwards, right? I mean, even this is a design choice, right? This is not cut in stone. You can have a memory prefetcher over here at the memory controller level that just looks at what row is open and tries to predict which cache blocks from that row you should prefetch based on the access patterns that you've seen in the past. Right? So where do you place the prefetcher, which we will talk about, actually has a big effect on how effective your prefetcher can be. Right? If you place it here, for example, it's just observing what's coming into the L2. It's not observing what's going into the I cache and D cache. Right? If you place it here, it's observing what's coming into the memory controller, the access stream that comes into the memory controller. It's not observing anything that happens over here. So your effectiveness depends on what you can observe. OK, let's take a look at these 4 questions. Basically, we're going to talk a lot about what addresses to prefetch. But we should always keep in mind, this is really important too, when to initiate a prefetch request. And where do you place the prefetch data? And how do you actually do this? And how is kind of tightly coupled with a lot of these, actually. But we'll talk about these. Let's look at the first one, what address to prefetch. This is really important because if you prefetch some useless address, you waste resources, right? And some of these resources are extremely important, like memory bandwidth. In GPUs, for example, today, if you're actually running GPU-like applications, you're memory bound. Your memory bandwidth is the biggest bottleneck. Even if you generate a few prefetches that are incorrect, you kind of reduce performance because you're actually taking away memory bandwidth from stuff that's useful. Right? That's one of the reasons modern GPUs, as far as we know today, don't do prefetching. In fact, if you try to talk to GPU companies about prefetching, they're scared of prefetching. That doesn't mean that prefetching cannot be useful in GPU context. You just need to do it really, really carefully. Cache prefetching also, like a useless prefetch also occupies cache or prefetch buffer space. And we'll talk about these 2 different things in a little bit. They consume energy. Energy is critical, right? If you're actually doing useless prefetching, you're actually wasting energy. And run ahead, this was one of the problems with run ahead, right? When it's useless, it's really wasting a lot of energy. Because it's not only generating a prefetch request, it's also consuming this entire core to actually generate all of those prefetch requests. And all of these could otherwise be utilized by demand requests or more accurate prefetch requests. And not all prefetch requests are equal also. Something may be accurate, something may not be that accurate, right? Depending on like what part of the memory space you're prefetching. That could differ. So accurate prediction of addresses to prefetch is really important. And one metric to use to evaluate prefetchers, in the end, the only metric to use to evaluate performance is performance, right? Execution time. But it's good to look at some of these auxiliary metrics, especially when you're looking at prefetching. Accuracy, for example. This is the number of used prefetches, demanded prefetches, divided by the number of sent prefetches. That's always a good thing. And we'll get to that in a little bit. So how do we know what to prefetch? Basically, most of the prefetchers work by predicting based on past access patterns, or by using the compiler's knowledge or the programmer's knowledge of the data structures and the access patterns. And we'll take a look at both of them. So what determines what to prefetch is really the prefetching algorithm. So we'll look at a lot of algorithms. But before that, let's talk about when to initiate a prefetch request. This is also important. Basically, again, with different algorithms, you'll have a choice. If you prefetch too early, then by the time you really need that data, the data might have been gone, right? Might have been evicted by somebody else. If you prefetch into the cache, for example. If you prefetch into some other buffer, that could have been evicted from that buffer also. This problem can happen in run ahead also, right? If you actually run ahead too far into the program, you may be bringing lots of stuff into the cache. And you actually, by the time you go back and need that data, those data, one of the cache blocks may be evicted, right? And also, actually, you may be causing pollution, right? This is tied to this part. Even if the address is accurate, if you prefetch too early, you may evict something that's going to be needed. And also, the thing that you prefetch may be evicted by the time you need it. So you're kind of killing yourself twice, right? Hammering yourself twice. You're evicting something that's useful, and the thing that you brought that you thought was useful is not going to be used because it's going to be evicted by the time you need it. Okay? So it's really important to prefetch at the right time. Prefetching too late is also not useful because it may not hide the whole memory latency, right? And in fact, it may not hide any latency if you figure out. For example, you generate a prefetch request, and in the next cycle, you issue a load that needs that request. You've saved one cycle. Sounds great, right? But then the memory latency is 1,000 cycles. So saving one cycle out of 1,000 cycles may not be interesting. OK. So when a data item is prefetched, this affects the timeliness of the prefetcher. So when a data item is prefetched, affects the timeliness of the and prefetcher can be made more timely by making it more aggressive. And we'll look at some examples of this. And when I talk about making the prefetcher more aggressive, it means that we want to try to stay far ahead of the processor's access stream. You can think of processor as having an access stream. It's generating requests this way. Well, let's do it this way. It's generating requests this way. And the prefetcher going ahead, right? And how far this distance is, the prefetcher is ahead of the processor's access stream, is really the aggressiveness of the prefetcher, how aggressive the prefetcher is. I'll give you an example on the slides in a little bit. For example, if you have a streaming access pattern, remember A plus 1, A plus 2, A plus 3, A plus 4. You can say, I'm always going to stay 32 cache blocks ahead of the processor's demand stream. Make sense? If you predict that you're actually streaming, you can say, oh, when I access A, I'm going to prefetch address A plus 32. When I access A plus 1, I'm going to prefetch address A plus 33. And if that's what's needed to cover the latency of memory, that's great, right? And actually, you can do this in software also. If you have a predictable access pattern, the compiler can decide where to insert the prefetch instructions such that the prefetch and the load has enough distance. There's enough stuff that's executed between the prefetch and the load. And by the time you get to the load, this prefetch is complete. Right? If the compiler knows enough about the access pattern, enough about the cache, enough about the latencies, it can potentially do that. Right? And we'll see an example of this. So one other challenge is where, right? Actually, this is an interesting challenge too, because assuming you do both of these perfectly, still you need to do this right. Where do you place the data, prefetch data? You can place it in the cache, or you can place it in a separate buffer. And there are advantages and disadvantages to both. So if you place it into the cache, it's simple, right? No need for separate buffers. The downside is now you can evict useful data, useful demand data, in fact. So this is called cache pollution. You can actually pollute the cache by bringing in something that evicts useful data. But if you have a separate prefetch buffer, you kind of don't disturb the contents of your cache. You protect the demand data from the prefetches, no cache pollution in this case. But now you complicate the memory system design. Right? Where do you place the prefetch buffer? That's the first question, right? When do you access the prefetch buffer? Do you do it in parallel or in serial with the cache? When do you move the data from the prefetch buffer to the cache, if you ever do it? You may want to do it when you hit the prefetch buffer, right? How do you size the prefetch buffer? This affects how much stuff you can store. And how do you keep the prefetch buffer coherent? We're going to talk about this, right? Cache coherence. If you have multiple things that are accessing the cache, if you have multiple copies of things in the cache, you need to keep things coherent. And this is one more thing that you need to keep coherent. OK? So these are actually not so easy questions to answer. And again, this is static versus you can think of this as a static versus dynamic partitioning problem. You can have cache that's partitioned dynamically between prefetches and demands. Or you can have two buffers. One is the cache that's dedicated for demand requests, and the prefetch buffer that's dedicated for prefetch requests. Now, if your prefetcher is really aggressive, maybe this buffer that you've dedicated to it is not enough. Right? You always have this problem when you statically partition these resources. So as a result of all of these different difficult questions, most modern systems, at least general purpose, they prefetch data into the cache. And you can read all of these papers about them. OK. After that, there's another aspect of where, which is which level of cache do you prefetch into? And I kind of alluded to this when we looked at that picture, right? Do you do prefetching from memory into L2 or L3? Do you do prefetching from memory all the way into L1? There are advantages and disadvantages associated with both, right? L1 is small. If you're actually prefetching really aggressively, you may be evicting useful demand data, right? L2 is big. It can probably accommodate more prefetches. L3 is even bigger. So the trade-off is how much you're disturbing the demanded cache blocks versus how much latency you're saving for a useful prefetch, right? Because if you prefetch into L1, and if you've done it right, the next time you need that block, you just hit an L1. There's no latency, right, other than the L1 latency. If you prefetch into L2, you still need to tolerate that L2 latency for that load. If you prefetch into L3, again, now your latency to access prefetch data increases. And can you prefetch between the levels? Also, L2 to L1. Actually, many modern processors have L2 to L1 prefetchers. Intel has some white papers. You can read about this. Where do you, and this is still not all of the design decisions. Let's assume you've figured out where do you prefetch. But then also, where do you place the data inside the cache that you're prefetching? Do you actually treat the prefetch blocks the same as demand fetch blocks? Because these are different, right? You do not yet know whether this is useful. You can gain confidence, certainly, right? You can say, oh, in the past, let's say you create a stream, A plus 1, A plus 2, A plus 3. And you keep reusing. You keep reusing all the data that's prefetched. And then you say, oh, this looks like I'll keep on the stream, so I'll treat this like a demand. But it may not always be the case. Basically, if you use the LRU policy without modifying it, you can place the prefetch block at the most recently used position. And you can actually disturb everything else that's in that set, right? Even though the prefetch may not be useful. OK? So people have considered skewing the replacement policy such that it favors the demand fetch blocks. For example, some processors, HPPA 8000, actually placed all prefetches into the LRU position. Whenever you prefetch data, you insert into the LRU position in the set. So if you get a demand access into the set, the first thing to be evicted is that prefetch block, because you insert it into the LRU position. Right? It's kind of giving low priority to prefetches in the cache. Now, this may or may not be a good idea. If the prefetch is really useful, and if you have that hot set, then actually you may evict a useful prefetch, right? So other people have looked at mechanisms for estimating how useful a prefetch would be and deciding how much priority they should give to the prefetched block in the cache. This makes sense. And some processors actually implement similar things. Simple versions, of course, yes?
We prefetch both from data and for both data and instructions.
That's right, yes. You can prefetch for both data and instructions. Instructions are an easier problem, actually. Yeah. And for example, instructions are more sequential in general. So a stream prefetcher, which we will talk about, basically A plus 1, A plus 2, A plus 3, that usually works really well for instructions. The difficulty comes from branches.
But then we put that in L1 instruction cache stream.
That's again a design choice, right? Yeah. All of the design questions apply to instructions and data. OK. I guess there's one more where, but we've already kind of discussed it. Where do you place the hardware prefetcher in the memory hierarchy, if it's a hardware prefetcher? In other words, what access patterns does the prefetcher see? So if you actually put the prefetcher such that it observes all of the patterns coming into the L1, you have the most complete information, right? It sees both L1 hits and L1 misses. So it sees a complete access stream of the core, which may be good. If you place it after the L1 level, it sees only the L1 misses. It doesn't see the complete access stream. If you place it further, it sees a smaller subset of the stream, because the stream that you see is filtered by the levels of cache that are above the prefetcher. Right? Now, if you see a more complete access pattern, if you're actually closer to the processor, this is potentially better for accuracy and coverage. Accuracy we discussed. Coverage is how many, so you have some number of misses that you have in the program. What fraction of those misses can you prefetch? That's the coverage of a prefetcher. It's different from accuracy, right? Accuracy says, this is the number of requests that I sent with my prefetcher, and this is the fraction that's useful. Coverage means this is the total number of misses I have in my program, and this is the fraction that I was able to prefetch correctly for. Okay? So if you see a more complete access pattern, that may be good because now you can find the patterns better. The problem with that is now the bandwidth into the prefetcher is much larger, right? Prefetcher needs to examine many, many more requests at the L1 level. Maybe you need more ports into the prefetcher, right? OK. So let's take a look at how again, and then we'll take a break, and then we'll start the survey of prefetchers. Do you do this in software, hardware, or maybe a combination of both? So in software prefetching, ISA provides prefetch instructions, and the programmer or compiler inserts these instructions. And this usually works well for regular access patterns, as we will see. Hardware prefetching, hardware monitors the processor accesses and memorizes or finds patterns or strides, and generates prefetch addresses automatically. And actually, both are used in existing systems. And execution-based prefetchers are also used. Here, basically, you generate a thread, a helper thread, let's say, that's executed to prefetch data for the main program. And this thread can be generated by the software programmer or the hardware, right? Or in a cooperative way. And you execute the thread in a separate thread context, either in a hyper-threaded or fine-grained multi-threaded or some kind of hardware context, or in some other core, right? You could actually execute in some other core that does the prefetching. And if these cores share some level of cache, you do prefetching into that level of cache, and this other core can benefit from that, right? So we'll take a look at that as well. I think this may be a good time to take a break for 4 minutes, and then we'll blast through lots of different algorithms. All right, let's get started. So let's start with software prefetching. These are 3 things that I mentioned: software, hardware, execution-based. So we're going to take a survey of some of these things. And software prefetching, here the idea is pretty simple. Compiler or the programmer places prefetch instructions to appropriate places in the code, right? And this is a nice paper that introduced one of the first implementations of software prefetching. This by Todd Mowry. That was his PhD thesis. He's a professor in the CS department, if you don't know. But basically, you have these prefetch instructions that prefetch data into caches. And somebody at the higher level can insert such instructions into the program, right? And this is one example of it. This is the x86 prefetch instructions circa, I don't know, 2010 or so. Maybe different right now when you look at the x86 manual. But the fundamentals don't change. What you have is you can actually prefetch data. And there are different types of it: T0, T1, T2, and NTA. Basically, these differ dependent on where they load data into the cache. If you look at this, T0 says temporal data, prefetch data into all levels of the cache hierarchy. And all levels are kind of weird. Again, it's microarchitecture dependent, right? It says Pentium 3 processor, first or second level cache. It's an or, right? It's not an and. Pentium 4 and Intel Xeon processors later on, second level cache. That's not all levels, obviously. First level is. And this kind of tells you that hardware manufacturers actually trying to give you some best effort prefetching, but they're not giving you exactly where the data is prefetched. So you cannot control where it's prefetched. In fact, you cannot even control that the prefetch happens, right? Because this is all only speculative, even though you may insert this instruction. For example, if there are no resources in the memory scheduler to place this prefetch request, maybe a good idea is to drop that request, right? Because it's all effort. It's a performance optimization in the end. It doesn't affect correctness. So there are different instructions for different cache levels here. NTA is non-temporal data with respect to all cache levels. This is for data that you're likely not going to access a lot. So for streaming requests, for example, you can use prefetch NTAs, and this instruction will prefetch data into the levels, but it doesn't disturb a lot of these. But in the end, the implementation depends on what the hardware designer chose to do it. The hardware designer can actually choose to ignore it, right? But you can actually get a lot of benefit from prefetch instructions today. There are other specifications from other processors. Let's take a look at how it works, though. Basically, it can work for very regular array-based access patterns. So let's take a look at this example. This example is a nice example where it can work, right? Basically, you have this. You're computing this sum. It's very simple. And you need A and B. But A and B can generate a lot of cache misses. So what you can do is something like this. Here, we're actually prefetching ahead for 8 iterations after, right? You're really prefetching the values that you're going to need for A and B 8 iterations later. And assume that these are cache blocks, right? You need to ensure that you actually do it at the cache block level, assuming the prefetch instructions work at the cache block level, right? Does that make sense? And how do you determine whether this should be 8 or 16 or 24? Well, that's the magic of the compiler algorithm, right? It depends on how big your cache size is, how large your memory latency is, what else are you doing in the loop to cover that latency. That's actually, you can imagine a complex equation, right? Ideally, if you would like to eliminate all of the misses in this loop, you would like to be able to prefetch ahead just enough such that whenever you really execute these instructions, they both get cache hits, right? Which means that the distance between how long the prefetch request will take and how much execution you will do to get to that instruction are the same. That's a tough thing to optimize for, right? Especially with processors that are out of order and there's a lot of contention in the memory system, right? OK, but anyway, if you actually do this accurately, this can gain a lot of performance. Now you can have the question, for example, how do you actually prefetch for the first iteration, right? Well, maybe you have another loop over here that's kind of inserted early on in the program, such that by the time you get to this loop, the first 8 iterations are kind of prefetched, right, in your cache. Does that make sense? Yeah.
Sometimes the cache block will be bigger than what you're trying to train. So would it be optimal to like unroll the loop until it's the size of a cache block so you don't have unnecessary?
Yeah, you could do that, definitely. And that's one optimization you can do. Now you're actually combining multiple optimizations to minimize the waste in the cache. Yeah. And some compilers do that, actually. People have explored unrolling plus prefetching together to maximize the utilization of the cache. OK, so there are issues with it. This works very well if you can actually predict the latencies and if the access patterns are regular. But one issue, even when you do this, prefetch instructions actually take up processing and execution bandwidth, right? Even when it works well. So that's one downside. How early to prefetch actually is difficult, especially when your programs get more complex, and especially when your latencies become unpredictable. It doesn't mean that it doesn't work, but it becomes much more difficult. Because the prefetch distance, how early you should prefetch, depends on the hardware implementation, memory latency, cache size, time between loop iterations. And once you actually optimize these for a particular implementation, the question always is, does it work for this other processor out here, right? And the answer usually is no, because that other processor has some other parameters. And this is true whenever you do optimizations that assume some parameters of the hardware, right? Because hardware is all different. And if you actually go too far back in the code to insert these prefetch instructions, now you run into accuracy issues, right? This is about where to place instructions. If you, for example, prefetch ahead 64 cache blocks, well, you run into maybe you'll actually not use them, right? Actually, in fact, when you exit the loop, you're guaranteed not to use the remaining 64 things that you prefetched, right? OK? So you need special prefetch instructions in the ISA, actually, for this. This is not as big of an issue, but because all ISAs today have it. For example, alpha, if you load into register 31, that's treated as a prefetch. It's kind of a cute trick, right? Because register 31 is 0, always. They've decided that's a prefetch. PowerPC has data cache block touch instruction, and you've already seen the x86 instructions. And this becomes more difficult, and this is always true. Whenever you have pointer-based data structures, prefetching is difficult. But it becomes even more difficult in software, especially if you want to do something like this. So let's say you have this while loop. Does this work? I guess it does, right? You're prefetching for 1 iteration ahead, assuming that this doesn't evaluate to null. If it does evaluate to null, you drop the prefetch, right? You don't generate an exception. So prefetches are, again, performance optimization. They're speculative. You don't generate an exception. But does this work? Now we are trying to prefetch 3 iterations ahead, right? Well, this one's hopefully better if it works. But it doesn't work, it doesn't work, right? Because if you get a cache miss over here, what do you do? Now it's not a, now you need to block to get that cache miss and execute it, right? It's not a prefetch anymore. OK? That's the difficulty of pointer-based data structures. Prefetching far ahead is difficult. Now you can have some other mechanism to predict this, but that may not be easy. OK, so I mean, we can actually talk a lot about this, but I'm going to skip right now. It's a fascinating topic, actually, how to do prefetching for linked data structures. It's a very difficult problem, but it's a problem where it's worth spending your creativity on. OK, where should a compiler insert prefetches? First of all, do you prefetch for every load access? This may not be a bad idea because it's too bandwidth intensive, right? Most loads hopefully hit in the cache. That's why caching works, right? You don't want to prefetch for all of them. So maybe a good idea is to, again, do profiling, right? Profile the code and determine the loads that are more likely to miss. And actually insert prefetches just for those loads that are more likely to miss. And then the problem is always representatives of the input set. If your input set is not representative, then you still may insert prefetches that are not going to be used. How far ahead before the miss should the prefetch be inserted? This is something we've discussed. Again, you can solve some of this with profiling, right? Profile and determine the probability of use for various prefetch distances from the miss, right? You say, if I insert the prefetch here versus here versus here, or if I say I prefetch for n iterations ahead, m iterations ahead, and z iterations ahead, this is what I would get when I run the program. You can actually do this, right? The compiler can actually generate multiple versions of the code with different prefetch distances. And it can pick the one that provides the best performance. Right? That's one form of profiling. Again, you always run into the issues of what is the profile input set is representative. And usually, you need to insert a prefetch instruction far in advance to cover hundreds of cycles of main memory latency. Right? So this leads to reduced accuracy, too, because you need to insert the prefetch instruction much earlier in the code. If you study this code a little bit, you will see that, right? If the latency of memory is 1,000 cycles, and the latency of execution of this loop is, let's say, 1 cycle, you need to really prefetch 1,000 cycles ahead, 1,000 iterations ahead. And your accuracy reduces because at the end, when you exit the loop, you've already prefetched a lot more ahead, like 1,000 iterations ahead, right? So you prefetched 1,000 things that you're not going to need. And that number depends on your memory latency as well as how much stuff you do in the loop. OK. But despite these downsides, software prefetching is employed by compilers, especially for regular access patterns. So you can actually enable, disable it in GCC. How many of you have done it? You've probably done it without knowing it, because if you do -03, it does enable prefetching, as far as I know. It may change, of course. -05, definitely. Yeah. But then it may not insert any prefetch instructions if you don't have predictable stuff, right, in your code. OK, so people have looked at hardware prefetching a lot also, because memory latency has been a really important problem. And the idea here is you have specialized hardware that observes the load store access patterns and prefetches data based on past access behavior. By the way, regardless of however much this area has been looked at, there's still a lot of thirst in the industry to figure out what are better prefetch algorithms. Actually, in a sense, this is an area that was less focused on. So people are focused on branch prediction algorithms a lot more than they focused on prefetching algorithms, even though arguably prefetching might be a bigger problem today than branch prediction. So it's a really good area to focus on if you want to actually improve performance relatively quickly, because memory is the big bottleneck. So trade-offs. When you have a hardware prefetcher, now you can actually tune it to the system implementation, right? You can actually design it into the hardware, right? And it doesn't waste instruction execution bandwidth, right? Because you're designing the hardware, you know all of the parameters, and you can tune the hardware to that. Whereas software, it's much more difficult to do that, right? The downside is more hardware complexity, of course, compared to software prefetching. Software can be more efficient in some cases because software has the ability to analyze the program offline, right? OK, so let's take a look at some hardware prefetchers. The simplest form you can think of is next line, whenever you access address A or cache block A, prefetch cache block A plus 1, and maybe A plus 2, A plus 2, A plus 3, A plus 4, A plus n, or n line ahead prefetcher, right? This is also called the next sequential prefetcher. And you do this potentially after demand access or after demand miss, right? So there are trade-offs associated with it. This is very, very simple to implement, which is nice. There's no need for sophisticated pattern detection in this case. You're just assuming that you're going sequentially. And whenever you access address A, you're going to prefetch the next n cache blocks. And it works very well for sequential or streaming access patterns. So instructions, for example, a lot of the processors in the past employed this kind of prefetcher for instruction prefetching. It was very simple, and you gain a lot of benefit because you're going to go sequentially in the program, at least for most of the time, right? You may break that when you jump somewhere else in the program, but maybe eventually you'll get back to the stuff you prefetched. The downside is it can waste bandwidth with irregular patterns, right? And even with regular patterns, let's take a look, right? If you have a stride of 2 and an n of 1, what is your prefetch accuracy? Trick question. You're prefetching always next line, where your stride is 2. Should I give multiple choice? Basically, address A, whenever you access address A, you're prefetching address A plus 1. But the next thing you access is A plus 2. 0, exactly, yeah, 0 in this case, right? If you change n to 2, what is your prefetch accuracy? 100%. Not the accuracy. Coverage is 100%, but accuracy is 50%, right? Because you're always prefetching A plus 1 and A plus 2, but you're only using A plus 2, which means that your accuracy is 50%. But hopefully, you're always covering what you're going to miss on. So your coverage is 100%. So it's hard to determine a good n, basically, even if you have a regular access pattern. If your stride is 256, forget about it, right? And actually, you have programs that have large strides, right, depending on how you allocate memory and how big your data structures are. And what if the program is traversing memory from higher to lower addresses? Well, this may be easier to fix, but it's not always plus, right? It's also minus. You may go backwards, right? Do you also prefetch the previous n cache lines? Now it becomes actually more difficult. So people have improved upon this. There are many different improvements. I'll cover some basics. But for example, one solution is figuring out which direction you're actually moving, right? You can say, oh, the next address I see is minus. So I'm going to use a minus thing. The next address I see is plus. I'm going to go that way. So people actually developed stride prefetchers. And this kind of, we alluded to it earlier in the in this lecture, actually, the striding value, right? It's similar. Here, if your address is striding, if your address is a predictable stride, try to figure it out and predict it. And you can do it on instruction program counter basis or on a cache block address basis. Let's take a look at the instruction-based one. Basically, you have this instruction at program counter, some program counter. You record the distance between the memory addresses referenced by that load instruction. That's the stride of the load, right? We've already covered the stride of the load, as well as the last address referenced by the load. And the next time you see this load, you take that last address, add the stride to it, and generate a prefetch. Make sense? So if the load is loading cache blocks A plus 5, A plus 10, A plus 15, ... You figure out the stride, which is 5. And when you access A plus 15, you prefetch A plus 20. It's pretty simple. And this is how you build it. I'm not going to go through this in detail, but you can imagine this is relatively easy, right? You have a table that is indexed by the PC of the load. It has the last address that's referenced by the load and the last stride. And you can actually have confidence bits saying how confident I am, right? By keeping a little bit more information. If you keep seeing the same stride 10 times, maybe you're more confident. But if you saw the stride only once, maybe you say, oh, I'm going to wait again until I see the stride again before I start prefetching. Right? That gives you a little bit more confidence. Because if you're actually flip-flopping between different strides, maybe you don't want to latch onto a single stride. OK. So there is a problem with what I just described just by doing last address plus stride. And that problem is the prefetcher may not be able to get much far ahead, right? You need to see the last address referenced by that load instruction in the previous execution of this load instruction, and add the stride to it. What if you executed the load instruction? What if you're going to execute the load instruction right after again, right? What if you're remember the loop that I showed you, AI plus BI? You're going to get to that load instruction again in one cycle, right? Or in a little bit. So initiating the prefetch when the load is fetched. So basically, you need to initiate the prefetch when you fetch the load in this case, right? You cannot go ahead. Because you need to see the load. Oh, I'm fetching this load. The last time I saw this load, this is the address it referenced. This is the stride. So I'm going to compute an address for it. Let me do a prefetch. But this may be too late, because the load will access the data cache soon after it's fetched. Right. So how do you actually solve the problem? There are actually many possible solutions. Let's talk about the prefetch ahead one. Well, instead of doing last address plus stride, you say last address plus n times the stride. Right? You're kind of emulating what we saw in the software prefetching. You're doing n executions ahead for this particular load. Or you can generate multiple prefetches. It's kind of similar to this, except you're doing all at once. Or you can do something called look-ahead PC. I'm not going to go through this in detail, but if you can somehow, one thing you could do, and actually some processors do this, maybe I'll go through it a little bit. You can decouple the front end from the back end of the processor. Oh, that's not what I want. OK, let's do this. So if you look at this, a processor has this front end. It has the branch predictor. And it's indexed by PC and some other stuff. And what the branch predictor does is it has some next PC, right? You can think of this as the branch prediction loop of the processor. And then after you do the fetch engine, you feed instructions. This is called, let's say, instruction queue, fetch queue. And then you can think of the rest as the back end. Well, if you have a good branch predictor, you can actually decouple this and run this ahead of the back end, right? You can keep generating branch predictions and run it much faster, maybe, even though the back end may be moving slowly because it has lots of cache misses and stuff. As a result, you'll be generating lots of PCs, right, to fetch from and fill the instruction queue with those instructions. Right? Now you actually know, maybe you have lots of instances of the same load at the same PC over here. And you can start generating those prefetches by feeding them into the backend. Right? That's one way of going ahead in the instruction stream, even though the backend may be stalling. Right? In fact, a lot of IBM processors have this. If you look at IBM Z series, they have this front end that's kind of decoupled from the backend. That way, they can generate better branch predictions as well, because they look ahead in the instruction stream. OK. There's another way of doing this. This is instruction-based. But you don't need to look at just instructions, right? Instruction-based kind of limits you, because you need to keep track of the stride on a per instruction basis. But the strides may be naturally occurring at the cache block level also, right? Like, you don't need to associate a stride with an instruction. But if you just look at the access pattern that you see in memory may be A plus n, A plus 2n, A plus 3n. Right? For a memory region, you can actually restrict the part that you look for a memory region. When you look at it, oh, I see A plus n, A plus 2n. And that's your stride. In fact, a lot of Intel processors operate this way. A lot of processors actually today operate this way. They look at the strides at a memory address level. Not on a, they don't associate the strides with a program counter, but they associate the stride with a memory region. In this region, my stride is 4. In this region, my stride is 8. In this region, my stride is 256. Right? And this is the idea of stream buffers, basically. Stream buffers are a special case of cache block address-based stride prefetching when n is equal to 1. So let's take a look at stream buffers a little bit. This is one of the first proposals in literature of this. Basically, the idea is you have these FIFOs, and it's called a stream buffer. And each stream buffer holds one stream of sequentially prefetched cache lines. Imagine that this A plus 1, A plus 2, A plus 3, A plus 4, A plus 5. And this is B plus 1, dot, dot, dot. And then C, D, E, F, G, H. On a load miss, if you get a load miss, you basically check the head of each stream buffer and see if you actually match. Right? If you match, then you actually get the data from there, because you already prefetched it. That's what this says. If not, you can allocate a new stream buffer to the new miss address. And as a result, you start prefetching in that address. And you can top off these FIFOs continuously with subsequent cache lines whenever there is room in the FIFO and when the bus is not busy. Does that make sense? This is kind of one very, very simple way of prefetching. Basically, you have these different streams in the program, and you're kind of filling in the stream buffer, assuming that you're going to go through this program. This works really well. For example, let's assume that you have two stream buffers, A starting from address A and address B. And whenever the bus is not busy, you're prefetching address A plus 1 and B plus 1, A plus 2, B plus 2, A plus 3, B plus 3, right? And if your loop is actually operating on A and B, whenever you need it, hopefully you have the data in the stream buffer. Does that make sense? Kind of like a vector processor also. But you can, of course, do more prediction. OK, I'll let you think about it a little bit. But this is the paper. It's actually the same paper that talked about victim caches, right? You remember victim caches? It's a paper that introduced two ideas, both victim caches and stream buffers. Let's take a look at how stream buffers actually work a little bit. Basically, this is the next address that you want to generate, and this is the increment. And +1 is a special case, remember, assuming that you're streaming through every cache block. And this is the CPU address. Basically, when the CPU and the core generates a cache miss, it compares this address with the top of the stream buffer. If it matches, it gets the cache block from there. And hopefully, if the CPU is going through this part of memory in a streaming manner, the next request coming from the CPU for this part of memory, this memory region, will be the next address in this stream buffer. And you can actually design the stream buffer this way, right? In this case, it sits after the cache. So whenever you get a cache miss, you search all of the stream buffers, heads, and figure out if there's a match. Existing processors actually have something that builds upon this, but much more sophisticated. First of all, you don't just do +1 stride prefetching. You can actually identify strides that are different. This is very limited, right? If you look at it, you can only do +1 stride. And also, the memory regions can be allocated more aggressively. We can talk about it, but you can actually read the papers related to this also. Actually, this paper that I'll briefly talk about has a good description of how many of the existing processors work. Unfortunately, industry doesn't publish papers that much on how exactly their prefetchers work, but you can see it from some papers. Any questions on this? It's pretty simple, right? You can imagine different algorithms also. Now you can actually build your own prefetcher that can figure out deltas that are +1, +2, +1, +2, +1, +2. Right? That's a good thing to think about, how you can build something like this that figures out that pattern in a very simple way. You can, of course, design a very sophisticated algorithm to do that. But what we're really interested in is doing this in hardware in a simple way. OK. Let's take a look at some metrics to evaluate prefetcher performance, and then we'll continue going into some other algorithms. The reason I want to discuss this is how far should you go ahead, right? In this case, like, how far should your stream buffers be? Oh, by the way, in many existing processors, stream buffers do not store the data. They just store the addresses, and they bring the data into the cache. That simplifies the process. If you look at this here, you need to search across all the stream buffers. But if the stream buffers just figure out which addresses you want to prefetch, then you load the data over here, and the processor just checks whether the data is present over here, the prefetch data. So how far do you need to prefetch is a key problem, actually. That's one of the difficulties in designing hardware prefetchers. And these three metrics are important. Actually, there are two other metrics, which we will talk about. Accuracy, we've already covered. This is the number of used prefetches divided by number of sent prefetches. And you actually computed the accuracy of a prefetcher, right? Coverage, we already covered this also. This is the number of misses that are prefetched divided by all misses that you see in the program. Timeliness, this is a little bit harder now. This is the number of on-time prefetches divided by prefetches that are used. Now, how do you define on-time? Right. If you eliminate an L1 miss, L2 miss, L3 miss, which one is on time? It's not clear again, right? Because this is not a binary value, whereas accuracy and coverage are binary values. But it's really timeliness in this case is, well, accuracy and coverage, you can actually incorporate timeliness into them also, then they don't become binary. But timeliness is you have this latency, and how much of it are you covering? OK, bandwidth consumption is another issue. This is memory bandwidth consumed with the prefetcher divided by memory bandwidth consumed without the prefetcher. The good news is if you're perfectly accurate, this doesn't need to increase. And also there's another good news. If there's idle bus bandwidth, maybe you don't care. Well, don't assume that. Assuming that there's idle bus bandwidth is a bad idea in today's systems. Cache pollution is another metric. It becomes harder to quantify some of these things in the end. These are you can quantify it as extra demand misses due to prefetch placement in the cache. Right? How much are you increasing the number of demand misses in the system? And this kind of has a loop over here because this affects your coverage, right? If you're increasing the demand misses, now you have more misses to prefetch for. And it's more difficult to quantify, but this affects performance. Ideally, you would like to minimize these two, maximize accuracy and coverage, and maximize timeliness, right? So prefetcher aggressiveness affects all of these metrics. And aggressiveness is dependent on prefetcher type, right? For most hardware prefetchers, actually for software prefetchers also, you can define a prefetch distance and prefetch degree. And I've already kind of showed you with my hands what a prefetch distance is. So let's take a look at it on the slide now. Prefetch distance specifies how far ahead is the prefetcher of the demand stream. Right? And prefetch degree is how many prefetches do you generate per demand access. And by increasing both, you increase aggressiveness of the prefetcher. So let's take a look at the access stream. These are the accesses that the processor has made. And now it's trying to access address X. If you have an aggressive prefetcher, well, this is the prefetch distance, basically. How far ahead is the prefetcher's predicted address stream is from the processor's access stream, demand access stream. If this is very close, then the prefetcher is conservative. If this is a little bit more, the prefetcher is middle of the road. If it's very far ahead, it's very aggressive, right? Okay. And prefetch degree is, let's assume that you have some distance. When you actually get a demand access, when you get the next one, how many prefetches do you generate? In this case, the degree is 3. For a given demand access, you generate 3 prefetches, right? Okay? And actually, they don't need to be consecutive. They can be strided, right? OK. There's actually a lot of things that I'm not covering here. For example, if you're going through the access stream, do you do it on physical addresses or virtual addresses? That's a good exam question for you to think, right? Like, how do you do on physical addresses? Well, maybe the physical addresses are not allocated contiguous, right? The pages are not allocated contiguously. When you get to the page boundary, let's assume that you go to the next consecutive physical page. Well, that's not what you need, because the program is operating with virtual addresses, right? Even though virtual addresses are consecutive, physical addresses may not be consecutive. In fact, you may get a page fault if you access that particular location, right? So how does the prefetcher interact with the TLB? No? Yeah, you had that question? OK.
Why do we do multiple prefetches for demand access anyway if we have a prefetch distance? Like, is that because it might jump?
Yeah, that's right. It may actually. So there are some reasons. That's one of the reasons. And that's actually another way of getting ahead. OK?
But then you're continuously getting more and more ahead. Like, then the distance is changing. Like, as long as that thing increments by 1 and this thing increments by 3, your distance will keep increasing.
That's right, yes. So you may actually want to cap it at some point. OK? OK, so how do these metrics interact? So let's take a look at very aggressive prefetcher, metrics meaning the performance metrics. A very aggressive prefetcher has a large prefetch distance and perhaps a large degree also. Very conservative prefetcher has a small prefetch distance and degree, which means that the very aggressive prefetcher is hopefully well ahead of the load access stream, right? And this has a positive, which is it hides memory access latency better, but it's also more speculative. Whereas very conservative prefetcher is closer to the load access stream. It may not hide memory access completely, but it reduces the potential for cache pollution and bandwidth contention. So the upside of very aggressive is hopefully you have higher coverage, right? You're trying to prefetch more, which means that hopefully you're covering more of your misses. And hopefully you have better timeliness also, right? Because you're farther ahead from the processor's demand access stream. But it's likely that you have lower accuracy, and you're consuming more bandwidth, and you're causing more pollution, right? Conservative prefetcher is the opposite of this. It's likely more accurate, not necessarily, but likely. It consumes less bandwidth, and it's less polluting, right? But it's also likely lower coverage and less timely, right? Because the processor will soon access the thing that you prefetched, likely again. Let's take a look at one metric, which is the prefetcher accuracy. And this is the percentage IPC, performance change, over no prefetching, performance in terms of instructions per cycle. And if you look at this, accuracy has a good correlation, actually. If you have a prefetcher that's relatively highly accurate, you gain, actually, a lot of good performance, 300% in some workloads, right? But if your prefetcher is not very accurate, you can lose a lot of performance also. And I'll give you one example over here. This is from this paper. This actually, if you want to learn about how some state-of-the-art prefetchers work, this actually describes those prefetchers. I'm not going to cover that in this course. But you can learn more, and you can see the sophistication. The principles are similar, but there's a lot of things that you need to handle. Actually, since you asked about distance, a lot of modern prefetchers have variable distance. They don't say, I'm going to be always 10 cache lines ahead. They basically vary that distance, right? And you can imagine what metrics you can use, right? If you're actually doing well in prefetching, you can actually vary the distance. Or maybe you can vary the distance based on available bus bandwidth. Right? OK, so if you look at this, basically here, this figure compares no prefetching, very conservative prefetching, middle-of-the-road prefetching, and very aggressive prefetching. On average, prefetching is a good idea, and very aggressive prefetching by slightly higher performance. In fact, a lot of workloads benefit from very aggressive prefetching. Some of these, for example, eQuake, it's an earthquake simulation. It's a floating point program that goes through a huge array and does it with a +1 stride. If you're very aggressive, that's good, because you're covering more of the memory latency. But some of these other poor guys don't benefit. For example, ART is another simulation program. Here, it turns out the stride is usually 3, and the prefetcher is not doing well capturing that stride, because there are other things that are confounding its mechanism to capture that stride. So you can actually lose a lot of performance. Basically, 48% decrease in IPC means you're doubling your execution time, right? OK, so how do you actually fix some of these things and make your prefetcher more adaptive? This is an idea that's employed in many modern processors, basically dynamically tuning the aggressiveness of the prefetcher, as I mentioned before. You can dynamically monitor prefetcher performance metrics and throttle the prefetcher aggressiveness up or down based on past performance. And also, you can change the location prefetchers are inserted in cache based on the past performance. For example, if your prefetchers are not accurate for this part of the memory region, maybe you say, for the prefetchers that are generated by this particular stream buffer, I'm not going to insert them. Maybe you can say, I'm not going to insert them into the cache, right? I'm going to insert them at the LRU position. Whereas this stream buffer has always generated, in the past, very, very accurate prefetches. So I will insert them at the most recently used position at high priority. OK, so you can actually come up with different metrics. And again, I'm not going to go through this in detail, but this is one potential heuristic mechanism. It's not necessarily the best mechanism. The design space, again, if you look at this, remember the fairness via source throttling? Remember we throttled the sources such that you reduce interference? This is similar, right? We're throttling the prefetcher to be less aggressive or more aggressive. And remember when I told you that whenever you have throttling mechanisms like this, you have a lot of knobs to optimize for? Well, you do have a lot of knobs over here, right? You can compute dynamically the accuracy of the prefetcher, either globally or per stream buffers. And based on the accuracy level, you can make some decisions. For example, if the prefetcher is low accuracy and it's not polluting, or let's say it's polluting, then you decrease its accuracy, decrease its prefetch distance, right? Because that's a bad idea. So basically, you can design hardware that captures whether the prefetcher is accurate, how late is the prefetcher, and how polluting is the prefetcher. And you can actually, by adding the right counters into your cache, you can actually figure this out, right? For example, one thing you will definitely need is a bit saying whether this block was prefetched or not. And the next time you access that block with a demand, oh, you know that that prefetch was useful. So you can actually increment the count saying, oh, this is an accurate prefetch. Right? You can actually figure all of these out. And you can come up with a mechanism that decreases or increases prefetcher aggressiveness based on some values for this accuracy, lateness, and the pollution that's being caused in the cache. And if you do that, you're doing much better. That's why some processors actually employ this. And how much do you do better? Basically, again, this is no prefetching, very aggressive prefetching. And ignore this dynamic insertion, dynamic aggressiveness. These are basically either whether you're doing insertion to the cache dynamically, like where do you insert, depends on how accurate you are, how polluting you are, and how late you are, or just doing aggressiveness throttling. But if you do both of them, you get the best performance. If you look at this, you're better than very aggressive prefetchers, and also you curb the downsides of prefetching. So this shows how important it is to do prefetching right. If you just do blind prefetching, just like what we've discussed earlier, you can actually hurt performance significantly, even though you may design a really good prefetcher. But by throttling, by doing adapting how you do the prefetching to the access patterns and to how good your prefetcher is doing based on particular regions, you can actually improve performance instead of losing performance significantly. OK. So I'll briefly talk over this, and then we'll stop, because what I'm going to cover will be much more than 4 minutes. So we'll start with prefetching next time. But we've so far looked at regular patterns, right? Stride, stream, prefetchers, they're all covering regular patterns. But there is a whole world out there that's irregular. Like you have indirect array accesses. You have linked data structures, which may be regular, by the way, but they may be irregular also. You have multiple regular strides, and we briefly talked about that. But you have random patterns also, right? What if you're doing a random walk on a graph? How do you prefetch for that? Well, I'm going to tell you some prefetchers that may potentially be able to prefetch for that. And how do you actually design generalized prefetcher for all of the access patterns? So next time, we'll start with correlation-based prefetchers that try to correlate between addresses and try to use that correlation to prefetch the addresses. Let's say your address access pattern is totally random, but you're always traversing A, B, C, D, E, F, G, H. That's your linked list. And you go back to that linked list. Well, if you kind of record the fact that after A, you access B. After B, you access C. After C, you access D. The next time you see A, well, you go back and say, oh, last time I saw A, I accessed B next, so I'm going to prefetch B. That's the idea of correlation-based prefetching. You're trying to correlate between addresses instead of trying to detect a stride. There's also content-directed prefetching, which we will talk about. This is basically, the basic idea is very simple, actually. Whenever you fetch a cache line, identify pointers in the cache line with the mechanism that I mentioned earlier in AVD prediction, and prefetch those pointers. Assume that those are addresses, right? And we're going to talk about pre-computation or execution-based prefetchers, how to generate these threads that can prefetch for the main program. And Runhead is one example of this, actually. Runhead is really an execution-based prefetcher. You can think of Runhead as a thread, right? Because it's actually a thread, because you're storing the context of the main thread in this checkpointed register file. And Runhead is a very speculative thread that keeps executing. And then you go back to this main thread from where you left off. So we're going to talk about these in more detail in the next lecture. Any questions? OK, I guess I'll see you Friday then.